Good morning. Let us resume our discussion. In the last class, we have discussed about key point extraction using Harris-Corner detector, Moravec operator, and we have seen some visual examples on applying the Harris-Corner detector for key point extraction. We have also noted its anisotropic response. We further discussed about at the key points, how do we extract some features or how do we describe the image or erase the information at key points. That is referred to as feature extraction at key points that we have seen through histogram of orientation gradients. So now let us discuss little more on histogram of orientation gradients. Both Harris-Corner detector and the histogram of orientation gradients. You should exercise to practice the computations on small examples. You should be able to say if we are given a small matrix of 5 cross 5 or so, you should be able to calculate what is the R value to identify whether it is a key point or not through Harris-Corner detector at a given point. So that you should be able to know, because as we have seen in the previous classes, R is nothing but a function of determinant and trace of the matrix M, and M comes from the gradients Ix, Iy, and convolution of gradients, correlation of gradients with respect to a averaging mask or a Gaussian weights. Okay. So you should be able to calculate M in terms of Harris-Corner detector, which is W convolved with or correlated with Ix square, Ix, Iy, okay, and then Ix, Iy, and then Ix, Iy square. So the process for this is first find out Ix, okay, Iy, and then Ix, Ix square, Iy square, okay, and then Ix, Iy. So you first find out all these images for the given matrix, then find out W convolved with Ix square, W convolved with Iy square, okay, and then W convolved with Ix, Iy. I hope you all know how to perform convolution both in 1 dimension and 2 dimensions. Once you get this, you will have a matrices. These will have 3 matrices, okay, one for each, and then you can use these 3 matrices. Whatever, if we are initially given 5 cross 5, these all matrices will be 5 cross 5. If I ask you to calculate the value of R and identify whether it is a key point or not at a given point, then what do we do? At this point, you need to calculate R using the formula, which is from M. You will be extracting determinant and trace, right? So determinant of M. This is based on the eigenvalues. Trace of M whole square. Okay, so this you should be able to do numerically also, if it is asked to compute the cornerless measure at a given point at all points, and then subsequently identify whether there is a corner or not at a given point in an image. Okay, so this you should be able to do on I would suggest that you take some examples and practice this. Okay. So, and then the other aspect that we are discussing we started discussing is histogram of orientation gradients. This descriptor also you should be able to compute for a given image. So if an image is given, as we discussed, histogram of orientation gradients involves what? First finding the gradient. Okay, that and then finding out the X and Y gradients and finding out the angle of gradient, and using that on the top of angle of gradient, finding out the histogram. So as we mentioned, first if an image is given, I of X comma Y. So for this, what we do, we can compute Ix. Computing Ix, Iy, I hope all of you know how to do that. I'm not telling it. So Ix means gradient in X direction. So which is again a matrix of same dimension, and that is obtained. How is that obtained? That's obtained finding out I of X comma Y minus I of X minus 1 comma Y at each pixel. Okay, so this is equivalent to convolving with what? This is equivalent to convolving with what filter or what kernel? I of x comma y, I convolve with what kernel? Can anybody tell? Okay, del of x comma y minus del of x minus 1 comma y. Okay, this is convolving with this. This is essentially convolving with this one, okay, in x direction for ix. In y direction it is 0. So it's essentially convolving with this kind of thing. Or if we write in 2 dimensions as well, or in, say, if we the equivalent of this is say this is 0, right, and this is minus 1 and this is plus 1. So if we are considering x plus 1 minus x minus 1, this is the kernel. But if we are considering x minus 1, then I think it's not necessary to write 2 things. It is necessary, it is enough to write 0 minus 1 0 0 0. Okay, so simply this is the kernel I, this is the filter. If we write actually hx is the filter, okay, then this is hx. Is this clear what I am writing here? If you would like to find out x directional gradient by a kernel like this, okay, so 0 1 minus 1 or minus 1 1. If this is the kernel, what will be I gradient ix x comma y? Can some of you tell, just to get the clarity on what we are discussing? Say instead of above hx, if I use the hx in this way now, so what will be the gradient? What will be the ix? How should I write ix? If this is hx, can some of you tell? How should I write in terms of I of x comma y now? If this hx is
I of x plus 1 comma y.
I of x plus 1 comma y, very good.
Minus I of x minus 1 comma y.
Very good. That's all. Okay. So this is how it comes. So in case if just to extend this further, in case if we have hx, so I am writing small h, but anyway you assume small h or capital H. Okay, hx is the kernel now, which is again 3 cross 3. I will make a little minus 1 minus 1 minus 1 0 0 0. Okay, 1 1 1. If this is the kernel, then what will be the ix? Can some of you tell? So any like anybody has an idea how will it be ix? Ix simply will be convolution with hx. But if you write it in terms of I of ix of x comma y at a given pixel, what it will be, then it simply be is equal to, so it will be, it involves a little bit more terms, x plus 1 comma y minus 1 minus I of x minus 1 comma y minus 1, okay, plus I of x plus 1 comma y minus I of x plus 1 comma x minus 1 comma y plus I of x plus 1 comma y plus 1 minus I of x minus 1 comma y plus 1. Hope you people understand how I am writing all this. Okay. Similarly, if we have something like hy, which is a vertical a kernel of something like this, okay, then what it will be? Iy now, gradient in y direction, x comma y, which is equal to what you can write if we write minus and plus. Yeah, how do I write this? I of
x comma y plus 1.
Y plus 1 minus I of x comma y minus 1. Okay, so this we are considering is y and this we are considering is x. Okay, this is positive x and this is positive. Given that we have written this. So essentially this is this, if we want to implement on the whole image, if the image is say 100 cross 100, okay, and then if you want to find gradient, one has to define first the gradient operator. Is it a simple differencing based operator or is it a little involved operator like this? or it is more like more robust operator, something like Sobel operator, which is say -1, -2, -1, okay, minus plus 1, 2 and 1, 0, 0, 0. This is HX in Sobel operation, Sobel edge operator. So is it a like edge operator that is given through a convolution kernel, or it is simply defined by a difference equation? So in either way, we can compute the edge or the gradient information in both x and y directions. Okay, so if this is I, we can compute actually first, we can compute and get ready with Ix and then Iy. Okay, both are of same dimension. Okay, and then what do we do with this Ix and Iy for computing HoG, histogram of orientation gradients? What we compute from Ix and Iy is G.
Angle.
Yeah, G we can compute if necessary. In fact, G is also used in HoG. I will tell how they use. G is the, if we consider G as the gradient, Ix square plus Iy square, this is gradient, magnitude, and then angle of gradient, if we define it as theta, it is tan inverse of Iy by Ix. So once we compute both gradient, magnitude and angle, assume that these gradient, magnitude and angle are given, and these also exist in terms of, these exist at each pixel. So if the original image is 100 cross 100, okay, these are also 100 cross 100. 100 cross 100 G image and 100 cross 100, what image now? Theta image. Okay, so given this now, what is the next step to compute HoG, histogram of orientation gradients? See, they, as I mentioned, there are different ways. One way is you can compute the histogram of orientation gradients for the whole image. If you want to compute for the whole image, simply what we need to decide? So we need to decide the bin size first. So bin size, for example, each bin is, say, if I say 10 degrees, and then if I want to compute from 0 to 180 degree, then what will happen? 18 bins will get, I will get. 18 bins if we get, then essentially what we will be having? 18 different values we will get here. Each value indicating what? Between 0 to 10, okay, and 20, 30 and so on. So 0 to 10, whatever I put in the first bin, 10 to 20 angles. See here at each angle theta, we can have the theta in the range in the degrees or in radians, but let's have it in degrees. And then we are considering this direction and this direction being same. Okay, if we consider that, then only 180 degrees. That means the positive and negative directions, we are not differing. We are just considering actually what is the direction, that's all. Okay, so then it is 180 degrees. So at each degree, you have actually 20 degrees. Okay, it's a matrix finally, 100 cross 100 matrix, 15 degrees. Okay, and then 50 degrees. Okay, and then 120 degrees and so on. Okay, so what we are doing here, we are counting the number of angles of that in that bin and making a histogram of orientation gradients. If this is for the whole image, if we are interested to make the histogram of orientation gradients for, say, each patch or each in the local neighborhood, okay, each image patch of dimension, say if it is 100 cross 100, assume that for each 20 cross 20, we would like to make a one HoG. And that HoG again, let's make actually the number of bins now, we can reduce to each say 20 degrees. Okay, so then how many bins do we get? So if we are up to 180, if we are going, how many bins do we get? If we go up to 20 degrees, yeah, we get 9 bins. So then 9 bins you have actually 9 cross 1 vector, and this is for each 20 cross 20. So how many 20 cross 20s will be there? So if we consider this is 20 cross 20, okay, how many 20 cross 20 days will be there in this image? Huh? So there are total number of patches is equal to how much? 25, right? So here 5, this side 5. So 25 patches. So total dimension of the HoG is how much? Histogram of orientation descriptor. With 9 bins in each 20 cross 20 patch is how much? Is how much. What we do, see, if you would like to get the whole description, what do? We concatenate the descriptor here, descriptor here, descriptor here, and so on. And hence what will happen? Each is 9 cross 9. So 9 into 25. This will be our the dimension. So it is 225. So 225 cross 1. Vector describes now the whole image in terms of its shape information at different locations. So here, for example, if a person is there, so if we have actually 5 bins here, okay, similarly, if we have here, wherever the person head is there, okay, you may have actually all angles. Wherever the hands are there, you may have actually some 45 degrees or 135 degrees angles. Wherever the other body is there, close to 90 degrees angle, you may get like that. Okay, so different regions in the image will have the different dominant directions, indicating what is the information content in that region. Okay, and hence this local histogram of orientation gradients is a powerful descriptor. Right? Hope this is clear. This discussion is clear. If you have any questions, you can ask. Otherwise, I will move on to some of the visual descriptions in terms of slides. Okay, and then we will move on to some other feature extractors, which are very well known and widely used in computer vision. Okay. Okay, so in the previous class, what we were discussing, so we have quickly gone through this. So now let us see with the dimensions and other things. So we have seen that for each 4 cross 4, we have a descriptor. Assume that each descriptor is of dimension, whatever. So here, I think 9 bins they made. Let's see. Yeah, 9 bins, assume that. For time being, assume 9 bins. Okay, so now let us take a practical problem. So given an image of 64 cross 128, okay, we want to see whether in this image is there a human or not. Okay, that is the problem. So these slides I have taken from Professor Jitendra Malik video lectures. So now if you would like to describe whether the human is there or not, we want to extract anyway shape information. So we would like to go for histogram of orientation gradients computation in the local patches, okay, in the local neighborhood. So now what we do is we would like to divide this image into 16 cross 16 blocks, okay, and then we want to have a 50% overlap in computing the HoGs, because see, on the boundaries, if there is some information, if we don't take with overlap, they will be lost. So we take with 50% overlap and then 16 cross 16 patches. So now 64, how many we get if we take with 16 cross 16, so with 50% overlap? Except at the boundaries, we roughly each for each 8 cross 8, there will be 2. For each 8 cross 8, there will be 2. Okay, so for each 8 cross 8, there will be 1. For each 16 cross 16, there will be 2. Okay, so total in this direction, if we consider how many will be there? 64 by 8 essentially minus 1, that is 7 we get. Okay, 7 like 50% overlapping patches will be there if you consider this 64. Is that fine? Okay, now along the vertical direction, how many we get? So if we go again with 50% overlap and then 16 cross 16, okay, how many we get? We get how many? 15. 15. Because actually 128, okay, by 8 minus 1, that is 15 we will get. Okay. So for each 8 cross 8, you can consider one. So like that. So it is accepted the boundaries, it is 15. So total number of patches we get, or number of blocks we get, where we are taking histograms is 105 blocks. And in each block, as we mentioned, we will decide a bin size. And how the proposed method by Trigs and Dalal is has made is they have taken this 16 cross 16 also into 2 blocks. Okay, so 2 8 cross 8 blocks, and each 8 cross 8 block they will have each cell is 8 cross 8. Within each 8 cross 8 they have made a histogram of say they have made a HoG vector. That means for each 16 cross 16, they made 8 cross 8, right? So 4 blocks they will get, 4 cells they will get. Okay, so the number of blocks is 125 and the number of cells is 4. And in each cell, 9 cross 1 is the histogram HoG dimension, considering bin size of 20 degrees. Okay, so 9 bins they have taken. So the total histogram dimensions now, if we see, is 105 into 4 into 9. That is this much, 3780 dimension. So hope you people understand how this number has come. And this is the dimension that describes the whole image now. Like this, they have described the all images in the training data set or in the test data set. And then what they have done, they have essentially trained a simple classifier using this as the feature vector. Okay, 3780 dimensional HoG vector as the feature vector. And then they classified it as human or non-human based on this. They trained, I think, SVM support vector machine, one of the classifiers, and classified it. Now, as you can see, the speciality of this is it encodes, in some sense, the local dominant direction. Okay, and then that information is already there in this. So that will help with the taking the shape information also into account. Okay, for classifying the objects of interest, here human or non-human. If we want to visualize how what HoG is capturing, what people will do is, in this say 9 cross 1 vector in a given cell, okay, in a 8 cross 8 cell, what they will see is what is the highest dominant direction, or what is the highest value in the histogram. Okay, so if the highest value is for 180 degrees, then it is dominant for 180 degrees. Dominant direction in that cell is 180 degrees. Highest value is 90 degrees, then the dominant direction is 90 degrees, like that. So that direction is what they will sketch here. Okay, so the sketching of this will visualize how the shape of the object is, and using this as a feature vector will help us to classify the objects. Hope this is clear. Any questions on this? Okay, so if there are no questions on this, let's proceed further. In computer vision, as I mentioned before, the main aim was to identify which are the good features for describing the objects, which are the good features that will help us to classify or to recognize an object better, and also to identify the features which are easy to compute. Because what usually happens is, as you can see, for a 64 cross 128 vector itself, 64 cross 128 image itself, for computation of HoG, we need those as many operations, okay, as you can see here. For each 8 cross 8, you need to compute the gradients. After gradients, you need to compute the histogram, and then you have to concatenate. Finally, for this itself, 3000 dimensional feature vector you had. And if you take a 1000 cross 1000 image, the dimension of that feature vector will be much, much higher. So in that case, handling, subsequently applying classifiers and so on is not very simple. So the focus was led to which are the simple feature extractors that are good in general and are also that are good for a particular given task. Say, for example, this is histogram of orientation gradients feature vector is generic in the sense that for any object, it encodes the shape information. But in all applications, this may not be necessary. There are applications, say, for example, mainly face detection or human-based applications, where we want to we know a priori that we want to detect faces only. And we cannot give a lot of time for detecting like the number of faces in a given image. Say if in a given image, if there are 20 faces, if the feature computation itself requires a lot of operations, and if you cannot do in a say minute, then many of the applications cannot be supported with that kind of algorithm. Because on the fly we would like to detect whether there is a person or not, and on the top of it we also want to recognize who is that person. So one of the very important application in computer vision was to deal with the humans, especially detecting and recognizing the humans and more human faces. So one example of such method now I will discuss, that is referred to as Viola-Jones approach for face detection. So this is the paper that I have discussed before, Dalal and Trigs, histogram of orientation gradients for human detection. This is what we have discussed just now. Okay, so let's see one example or one application example with the key point extraction and description, and then move on to the face detection that we thought of. See, we can see a direct application of identifying the key points and then matching in panoramic view creation, or when we want to stitch several images taken at different slightly non-overlapping, but at different locations. How do we stitch them? As we discussed at the beginning, this is also referred to as image mosaic. So first take the image 1 and image 2, extract all its key points or identify all its key points. So you see that as all the corner points are the very distinguishable points from the neighborhood are all marked with red here. So these are all having, actually, if we consider Moravec operator, R greater than threshold. Okay, similarly, there are other key point extractors like scale invariant feature transform, which I will discuss subsequently. So that also gives a good feature points. In scale invariant feature transform, what we do is we try to find out the key points not only at a given scale of the image, but also at several scales. The reason being, different objects will look better in different scales. For example, if you see the building, this may be good in this bigger view. When say if we downsample, it is easy to detect even the corners in the big house or big building. But human face, on the human face or on the humans or on small objects, if we would like to extract features from this image, then we need to do it at the higher scale. So there is different, if we see the image at different resolutions or different scales, what we mean by scale here is spatial scaling. So it is say 100 cross 100, 50 cross 50, 25 cross 25, and so on. Different features gets highlighted well. Okay, and then we want to extract key points, identifying key points is also easy at different scales. Further, any key point which is a robust key point has to be stable across the scales. That means at least, say if a key point identified at 50 cross 50 should also be identified at 100 cross 100 and then 25 cross 25. Similarly, a key point identified at 25 cross 25 should also be identified at 50 and at 12.5. Okay, like that. So at least across the neighborhood scales, okay, the key point or the distinctness of a point should be consistent. Okay, so that is being checked by the scale invariant feature transform. Is a key point invariant to scale to some extent, and also we take these key points at across scales. Okay, and there is also a efficient way of this, like making these key points identified. Taking as we mentioned before, a Laplacian of Gaussian, implementing that very efficiently through differential of Gaussian. So we will discuss that subsequently. And also the HoG feature extractor that we have discussed will also be a part of this scale invariant feature transform. wherein the scaling invariant feature transform takes this descriptor with respect to the orientation of the object. That means, say, for example, if you want to describe this key point, then better take a patch, something looking like this. Okay, like this. So the orientation of a normalized histogram of orientation gradients is what is considered in shift. So those we will discuss with little more details later. For time being, assume that we have got the key points and we also have the descriptors around these key points. Now the question is, I want to make a mosaic of it, in the sense that I know that this person, okay, and this person is same, okay, and similarly this region and this region is same, okay, this is 1 and this is 1, okay, and then this is 2, okay, this is same, but I would like to match them. And using this match, say, assume that if I have got key points, say 3 corresponding points, okay, assume that I have made this also one more corresponding point. Given this, can I make a global transformation to the image 2 from image 1? That is the question. See, global transformation means this, let this be in I of x comma y. Okay, x comma y Cartesian coordinate system. This may be in x dash comma y dash Cartesian coordinate system. Okay, that means this may be with respect to this xy Cartesian coordinate system. This x dash comma y dash may be rotated or translated. Okay, and somehow they are related globally, in the sense that because we are taking with a camera, the camera may be rotated like this, or camera may be translated like this. So the relation between x dash y dash and xy can be captured through a kind of rotation and translation in a simple sense, and it may be captured through little more complex transformations, but however it can be captured. So if we assume that xy, each point, spatial point in first frame and each spatial point in second frame, okay, are related by a transformation with either rotation, translation, or a composition of rotation, translation, and shear, and so on, okay, which is referred to as affine transformation here. Okay, so I'm just writing an example of transformation. This is referred to as affine. Okay, so there in A1, A2, these are what are A1, A2, A3, A4? Defining the affine transformation. Okay, and then these in turn define the rotation, scaling, shear, translation, all those things. Okay, putting these two together, what we have is the global transformation between image 1 and image 2. But to compute this, who will give us A1, A2, A3, A4, and B1, B2? We have to compute from the corresponding points. Say if I know that, actually, say if I identify that I1, okay, x comma y is corresponding point with I1 x dash comma y dash. How do I identify a corresponding point? See, I assume that I identified 4 corresponding points here. Okay, maybe 40 corresponding points here. I might have identified 50 corresponding points here. I try to find out the match, okay, with a descriptor around the corresponding point, and then see which is the best match. So 1, 2, 3 are matched with 1, 2, 3. Okay, assume that here. Now I have identified corresponding points. I1, I am matched with I1 dash, I1 x dash comma y dash, and I2, okay, assume that I1 is matched with I2 x dash comma y dash. I2 is second image. Okay, I1 is first image. Assume that. Okay, I1 is first image, I2 is second image. Okay, and then similarly, I1, I2, sorry, where do we put? I11 we say. Okay, I21. Okay, I11, I12, x comma y, again matched with I hope you people understand what I'm telling here. I22 x comma y, x dash comma y dash, and again I13 x comma y matched with I23 x comma y. Here x dash comma y dash. Here x dash comma y dash indicate the coordinates. Okay, in respective frames. I1, I2 are images. The superscript is indicating the correspondence. Corresponding, okay, point. Which corresponding point it is? Index of corresponding point. Okay, so hope this is clear. So now given this, how many corresponding points are required to identify A1 to A4 and then B1 to B2? Any answer for that? Assume that if you would like to identify the affine transformation parameters, how many key points are required? How many are required? So one is sufficient, one corresponding point, or two are required, or three are required? Any answer for that? I need some answer.
One is sufficient.
Okay. Why one is sufficient? See, if we have one, how many equations will it give? If I assume that if you have only one, how many equations do you think it gives? Given this transformation. See, somehow identified.
Two equations.
Yeah, it gives only two equations. So I know that this x, say if this value of x dash x1 x comma y is say 10 comma 20. Okay, and this value is 10 comma 15. Then I know that actually this I have one equation. Okay, this second point, for the second point it is at different location. So this value will be 20 comma 35, and this value may be say 25 comma 30. Okay, and then it gives another two equations. How many equations are required to solve A1, A2, A3, A4 and B1, B2? How many variables are there to solve for affine transformation? How many variables?
6 variables.
Yeah, 6 variables. To solve 6 variables, how many equations are required? Each correspondence point gives 2 equations. Okay, each corresponding point will give 2 equations. And how many equations are required now total? Or how many corresponding points are required to solve 6 variables?
3 corresponding.
Yeah, 3 correspondences. Minimum 3 correspondences are required. Okay, so with minimum 3 I can solve. Of course, if I may have more in general, if I have more, then there should be some methods to see which are good to take. Okay, that means say I should be able to throw away some of them which are not very good matches or corresponding points. And I should, if I found that finally after throwing away some outliers in the sense that which are not very good corresponding points or which are not reliable equations, then what I do, I relay my computation on the rest of the sort of like more confident corresponding points. If I get 30 corresponding points, I will propose the method to solve with 30 equations and 6 variables. Or will I be able to solve it or not? Or do you have an idea on how do we solve if we have more equations and less number of variables? Yes or no? Have you solved anything? Have you solved anything in mathematics? Yeah, pseudo inverse will come. That we will see later. If at some point of time, we will also discuss how to throw out the outliers if time permits. And along with that, we will also see how to solve when we have more equations. So this is typically is done to find out the global displacements, okay, or global transformations. Okay, these are referred to as displacement models between image 1 to image 2. And the displacement models can be simply the transformation, global transformation. Or displacement models. Global transformation can be captured through simply a translation. Okay, or then a little more rigorously by rotation. If we capture through rotation, it is referred to as, and translation, it is referred to as rigid body transformation. Rigid body transformation means it is a rigid body. That means within the body there will not be any deformations. Okay, and however you may have actually it is rotated or translated. Okay, so the body as a whole will move. The pixels within the body or the objects within the body doesn't change their distances. That is rigid body. Okay, so we can model it as rigid body transformation with rotations and translations, or it is with affine. Also, as you can see here, in affine, whatever we have written here is written in terms of equations. Are you able to relate between the equation kind of nature of relation that we have made between x and y, x dash and y dash versus the equations? Hope you can relate them easily, right?
Yes, sir.
Right. Or displacement model. Okay. So we can also see a little more sophisticated transformations, because what's happening is, see, these are all the 3-dimensional objects. We are projecting onto 2-dimension. So on the top of, say, rotation, translation, and then even shear, okay, there will be other transformations that happens because of the projective transformation, in the sense that, say, if you see a road, okay, even though the road lines are parallel, okay, that means the road ends are parallel, but when we see it, what will happen? They appears to be converging at a long distance, right? So that is because of the perspective effect. If you see a textured pattern, what will happen is the texture at the, when you see at the near to you, they look bigger squares if it is a square texture, and at the far you can see that smaller squares, they all look like a cross lines converging. Okay, that's because of the perspective effect. Okay, so such effects can also be captured through a little more number of parameters relating x, y, and x dash, y dash. Similarly, there are some suboptimal ways, because this involves division, which is a little difficult to identify mapping between x dash and y dash to xy. So there are some biquadratic, bilinear, and pseudo perspective kind of projections. These are all referred to as projections models. And which will relate the image displacement from one image to other image, or the object's displacement in one image to other image, in a global sense, okay, not individual sense. Okay, these are all induced through the camera position change or camera location change. I think it's going somewhere. Okay. So any questions so far on this? So once we use such a transformation matrix and identify A1 to A6, okay, then or A1 to A6 or A1 to A4 plus B1, B2, what we can do is we can apply FN transformation. That means second image we can align. So previously it's in I of x comma y, and then this is in I of x dash comma y dash. So one way to do is we can make actually first image to I x dash y dash coordinates, okay, or we can make this to xy coordinates. One of them we will make into the other coordinates, and then we put all of them in the same coordinate reference frame. Okay, one of the reference frame we take as reference frame, and the other coordinate frame is aligned to that. So then what will happen? This, you can see that the information gets stitched. Wherever the commonness of information is there, there we will average. And this, you can see that the panoramic view we can obtain, or mosaicing can be done. So this is one of the technique of using the key points and then the point descriptors in computer vision to match or to make a panoramic view from the different images at different viewpoints. Okay, so this is this discussion on directly using the key points and the features for a application of computer vision application. Now let us see how different kind of feature extraction methods have evolved, especially as I mentioned, for an application of importance like face detection. So let us see, let's get the basic idea in this class, and we will further discuss on it in the next class. See, assume that we want to detect faces in an image. This is a very important application, as I mentioned, because say we in all our cameras now, if you see, okay, the face detection is almost real time, and we would like to have it. So detect how many faces are there, and then we also want to identify where the faces are. Okay, and later we also want to recognize also in some of the many applications. So for detecting face, what, say if we have 1000 plus 1000 images, okay, maybe here 1000 plus 2000 images, and face assume it to be a patch of, say, for ease of computations, assume that 25 cross 25. Okay. Face can be there in 25 cross 25 patch. Assume that. Now, how many? Let us understand the complexity of the problem first. How many number of patches I have to scan to identify whether there is a face or not? How many patches I have to scan? That means that, say, each I have to keep sliding it, or in a overlapping or non-overlapping fashion across the whole image, and see each patch, is it a face or not a face, right? So if I want to do that, how many patches we need to see? So it is 25 cross 25, right? So how many? 40 here in this side and then 80 in this side, right? So total how many? 3200. 3200 patches I have to see. Am I correct? At 3200 patches, I need to see whether there is a face or not. Okay. Is it sufficient? Is it sufficient? The answer is no, because some of the faces can be small, some of the faces can be big. Okay, you here the example, in this example, it is not very well seen, but some of the faces can be very big. Okay, somebody can be here. Okay, and then somebody can be very far. Okay, if we see in a crowd, it will be much more difficult. So you need to see across different scales. How many scales? Say, assume that I want to see across five scales. Okay, 2 plus this side, then 2 bigger side, 2 smaller size. Okay, so 5 scales. So across these many positions and then across these many scales. Is that enough? We also may wish to see if in between these two regions, if there is a face, we will miss it, right? So we should see with some overlap as well. So assume that we put 50% overlap into 2 for overlap. This for scales. Is this enough? Huh? Is this enough? This is still not enough. Because somebody will come and he will put his face like this. Okay. And then the face will be something like this. So we have to see with angles. Okay. Assume that if we put some angles, okay, that also we have to consider some rotations. So probably I think if we consider this and this 5 degrees with some, say, 10 degrees, this side, 10 degrees, that side or so. Okay. So maybe another 5. So this amounts to how many number of scans. That means each scan we have to see, each patch at these different instances, we have to see whether it is a face or not. So roughly this comes to how much? 25, 50, okay, and then close to 10 power, assume that 10 power 5. Okay, order of 10 power 5. Okay, and at each location now, we have a 25 cross 25. We need to see whether it is a face or not. So how many operations are needed if we consider HoG? Okay, of 9 bins. Okay, then the feature vector consists of 10 power 6 feature vector. Anyway, feature vector is 9 plus 1 only, but we have to make an operations of order 10 power 6. And with each feature vector, we have to give it a classifier. So it is almost impossible to see whether there is a face or not in a given image. Now, how many frames do we have per second? Okay, 30 frames per second. Okay, so and if you would like to demonstrate in real time, at least we should have actually 4 or 5 frames per second, or at least 1 frame per second in terms of results. So it is very hectic, or in the sense that it is not easy to make a real-time application of face detection. So we should have very simple features to perform such a task. Okay, and what are the such simple face features is being investigated by Viola-Jones, and they have come up with very nice or simple features. The simple features are like this. We get the idea of features and then we'll conclude this class. So see, in the if we see face, what are the distinct things? Usually in the face, okay, there will be a region where ice region, you can see that it will be darker, okay, compared to the other region. So this is darker, okay, compared to either this region or that region, okay. So and then the if we don't have eye glasses, more specifically, okay, this region will be brighter compared to these two regions. Now in this, so these are some of the identified features in a face. So that is brighter, darker, darker. Okay, again darker, brighter. Okay, so bright or dark, to identify, it is enough to see a binary mask. Binary mask in the sense that just I will make a difference. Okay, brighter minus darker, if it is higher, I say that the response at that location is high. If that response at that location is high, there is a likely that there is a phase or there are eyes there. Okay, so essentially they have used these kind of features, which are referred to as just simply algebraic difference. So in the feature, now the filter that enables us for feature extraction is all like 0 here and 1 here. Okay, for one first feature kind of features. Second kind of features, what do we have actually? 1 here, 0 here, or minus 1 here, just to be even more better. Okay, and then minus 1 here and 1 here. So you people understand the principle? With this, if I convolve over the whole face, with this also, if I convolve over the whole face, at the eyes region, this gets highlighted. Again, at the eyes region, eyes to nose region, this gets highlighted. And if I identify high response for this kind of feature vectors, okay, I see that there is a phase. And to make this at different scales, what I do, initially this may be say 2 cross say 1. Okay, that means, 2 rows and 1 column. Later, what I may do is I may make it actually 2 cross 5. Okay, and then 2 cross or 4 cross. Okay, 4 cross 10. So we can make actually the same kind of filters at different scales and then convolve to identify the faces at different scales. Okay, so like that, what the proposition by Viola-Jones is to use simple set of features. Only just post plus and minus operations, which are quite easy to do. No multiplications even. Okay. Second thought for them is to compute these very effectively over the whole image. We need some kind of an effective technique. Okay, so they also propose subsequently a nice way of computing these features. But these features alone are not sufficient. So they extract few more features and then select among different features that they have proposed, which are the important features, and then use them for face detection. So in the subsequent classes, I will give some of the hints on how exactly the algorithm is built upon. And then subsequently, we will move on to some other feature extraction techniques to conclude on the basic methods that are used in computer vision. And then we will go to the computer vision applications. Okay, some of the tasks like we have discussed in computer vision and then deep learning aspects. If you have any quick question, you can ask. Thank you then.